everyone. It's a real pleasure to introduce Manuel Vázquez, Professor Manuel Vázquez. I have a long list about his achievements, but I will mention just some of them. Manuel made his thesis in the University Complutense of Madrid. Then he gained a fellowship, a Humboldt fellowship, for work at the Max Planck Institute in Stuttgart. He works also in Technical University of Denmark, and after some years he come back to Spain. He was the head of the laboratory of the Institute of Applied Magnetism, that depends also on the UCM, Complutense of Madrid. Then he established the group of nanomagnetism and magnetization process here in the institute. Regarding the management, he was the manager of the Spanish Strategic Action on Nanoscience and Nanotechnology. He was chair of different congress, but in particular, he was the main chair in Intermag and in the International Conference of Magnetism. He was secretary of Magnetism Commission of the UPAC, co-founded of the Club Español of Magnetismo, founded of the IEEE Magnetic Society Spain chapter. He received the Salvador Velayos Award. He was president of the IEEE during 2 years. And he received also the IEEE Magnetic Society Distinguished Service Award. Apart of that, he supervised 35 PhD students, many visiting students, just PhD to professors. He co-authored 300 publications and several books, and especially he was the editor of the Magnetic Nano and Microwires that have two editions. And well, in summary, he worked a lot for the magnetism in Spain and the magnetism in the world. And now I think that he will talk about nano and microwires. No sé dónde está.
It is a very good opportunity for me to give this talk, somehow also profiting of the opportunity to introduce some of the activities, research activities we have been made in the a couple of minutes more at the end. Okay, now I hear also myself better than before. So this is a summary of the talk. I will be talking about two families of magnetic wires, micro and nanowires, depending on the diameter of these wires. Micro wires, when they have roughly 100, from 10 to 100 microns in diameter, and nanowires from 20 to 200 nanometers, roughly. And the objective of the talk is to underline the role played by the cylindrical geometry in the magnetic properties, domain structure, magnetization reversal process, and particularly on the applications. I will emphasize particularly the different applications that we have developed with micro and nanowires. So this is a picture of the laboratory for ultrarapid solidification to obtain amorphous wires. So we have three machines, three rapid solidification techniques in the laboratory, and I would like to underline the role of Alejandro Jimenez and Alfredo Hacker. They are working very nicely in the last time to improve, to optimize the machines. So this machine originally is from the Soviet Union, but now is much more simplified. So, I will be talking about the in-water quench amorphous wires with diameter in the order of 100 microns, and glass-coated amorphous wires with the diameter in the order of from 1 to 30 microns, covered by Pyrex. I would like to say that, to summarize, in both families of microwires, which is important is the composition. The magnet.
Yeah, you can try this one. Morgan.
Ir viendo ¿me oís bien?
Pégatelo mucho aquí, ¿vale? Y ya está.
No, ya está. Lo podéis ir viendo el vídeo.
Pruébalo ahora, a ver.
¿Sí? Yo no sé si se oye mejor con esto. ¿Sí? Bueno. Como veis aquí, ¿cómo fabricamos? Hay dos vídeos, voy a poner solamente uno. Glass coated microwires. The magnetic core is in the order of from 1 to 30 microns in diameter, and they are coated by Pyrex, insulating Pyrex. And it's a very manual process. It's very tricky. So it's not everybody can make that. So in fact, it takes some time to get expertise in that. So this video was recorded by Pedro Mendoza. You remember him from Argentina, with Giovanni. This is, you see the hands of Giovanni Badini, Confalonieri. Okay. Do you want me to put again the video or no? No. Okay. So as I mentioned, the very important characteristic is the composition. The composition determines the magnetic response. When there is iron rich with high and positive magnetostriction, we have a uniaxial magnetization direction is along the axis of the wire. For negative magnetostriction, which is cobalt rich composition, we have a circumferential distribution of magnetic moments, the magnetization. So this is nearly an hysteretic magnetic response. Here we have the magnetic bistability. And for nearly zero magnetostriction, cobalt iron alloy, they have the so-called giant magnetic impedance behavior with the largest initial susceptibility that is very interesting for many particular applications with the wires. Just very roughly, which is the interpretation of this bistellar magnetic behavior? We have this square loop it is practically impossible to obtain an experimental point in this giant Barkhausen jump. And the interpretation is that we have a core with axial magnetization, as I mentioned before, and then we have a single domain nearly, but in the very ends of the microwire in the remanence. When we apply that particular value of applied field, that we obtain this giant Barkhausen jump, a domain wall moves very fast from one end to the other to get the opposite situation concerning the magnetic domain. And those with cobalt iron silicon bore alloys with zero magnetostriction, they have the so-called giant magnetoimpedance effect, which is relevant in many sensor applications. I would like to say that although we have been working with this for almost 30 years, there are still very interesting work experimentally to measure, to determine the magnetostriction constant of these alloys. So just changing a little bit the composition, we get a magnetostriction from positive to negative, and this is probably the smallest value that has been measured concerning the magnetostriction. I'm not going to talk about magnetoimpedance, but if somebody is interested, we can talk later. Measuring this, the hysteresis loops of these microwires is apparently very simple. So with we apply the magnetic field along a solenoid, for example. We have a number of pickup coils to obtain the time evolution of this magnetic domain wall I mentioned before. So when in this in these secondary coils, we get a signal when magnetization, when this domain wall is passing these pickup coils. So we have two subsequent peaks, and from that as we know the distance in time and the distance between the secondary coils, maybe 1 centimeter, something like that, we can get the velocity of this propagation, of this propagating domain wall. This is an experimental result for the velocity of the domain wall as a function of the applied field. We can reach up to around 1 kilometer per second. Well, years ago we studied the equation of motion of this domain wall. I'm not going to pay attention to these, well, the equations, because maybe it's not so interesting now. But I would like to explain a very simple experiment to control the position and velocity of the domain wall. So we have a solenoid to generate the axial magnetic field. We have two pickup coils symmetrically placed with regards to the ends of the solenoid. And we have, in addition, a local field coil. This local field coil creates a magnetic field that opposes the main field generated by the solenoid. And also, very importantly, the magnetic wire is asymmetrically located inside the solenoid. You see here, one end is outside the solenoid and the other is inside. With this, we are ensuring that this domain wall is nucleated in this end, because here the field is larger than the other end. So we generate a domain wall here and moves to the right. And this is an schematic view of the domain wall during the motion. Okay. So years ago, we were able to control the velocity of this domain wall, just playing with the value of the local field in the center of the solenoid. So we are able to somehow to reduce the velocity and to stop the position of the domain wall in a particular place. So you see the experimental and calculated points. So this is important because we can control not only the velocity of the domain wall from 1 kilometer per second to very small values, but also we can stop the domain wall in a particular position. Also, I would like to some very recent results by Esther and Rafa Pérez del Real, where they have been able to obtain the time-resolved domain wall velocity. So this is the velocity of the domain wall when just after an application of a pulse of magnetic field. So we have the velocity, in this case is 1200 meters per second, from the nucleation up to the annihilation of the domain wall when it reaches the other end. So, but when we applied a local field, we are able to see this very locally. We see that the velocity decreases just in the position of the central coil. So, and depending on which is the values of the local field, we can obtain smaller values of the velocity and finally to stop in a particular position this domain wall. This is velocity as a function of time, and this is the velocity as a function of the relative position. Well, now I would like to give some examples of applications with these microwires. So this, for example, this microwire has a magnetic bistability with a square behavior. But if we are able to distribute a number of microwires nearly parallel to themselves, so the screen is planar, so the wires are really parallel. Okay, so you see that the response is completely different. It's completely different because of these magnetostatic interactions. So it is very important, these interactions, to control the magnetic response of an array of a set, no, more than an array, a set of microwires. So this enabled us to develop a patent for encoded magnetic card with a number of different wires, each one having a different switching field. So we have some kind of digital code for depending on the distribution of magnetic wires. Another application also years ago, so is using a microwire for magnetoelastic signature authentication. So we have, this is a normal pen with a microwire in the axis. So when we have a spring here, so when we are writing, we are making some mechanical stress to the magnetic wire. So this wire can be magnetostrictive. So if we have some cables here inside and we have a signal, we can get the signal from the microwire outside. And this is a typical magnetoelastic signature. You see, when you are writing, you are making some mechanical stress, and this is your signature, characterized by a number of peaks. So depending on the person, maybe you can copy some signature, but the magnetoelastic signature is nearly impossible to replicate. But importantly, I would like to comment that each person has his or her own magnetoelastic signature, but depending on whether you are very happy or not so happy, your signature is not the same. So what is important is not the total duration of the signature or even the amplitude of the peaks, because if you are very happy, maybe you are silent with making a strong mechanical stress. So the amplitude of the peaks can be very large. So what is important is the number of peaks, and this trend of peaks is characteristic of each person. Another application very, very recent in collaboration with, so actually we supply these microwires to the people in Dresden. They are interested to generate here very locally a strong gradient magnetic field. So we have 4 microwires, actually with some coils at the end, so to generate a single domain structure in each one. So, and depending on how is the coupling of the different magnetic field, we can get a quadrupole or biaxial magnetic fields just in the very center of this disposition, which is used by these people for very attractive applications. Years ago, we also, in collaboration with people in Max Planck Institute in Halle, so we passed them a magnetic tip with non-magnetostrictive microwires for spin polarized scanning toric microscope. And this is an example. This is a domain wall in a cobalt thin film. You see this is the domain wall, and we are in 2 different domains. So it's really so the width of the domain wall is 1 nanometer. So it's really very, very sensitive. But also we have had different collaboration with other groups. For example, to develop sensing elements, microwires as sensing elements for orthogonal flush gates. Or also we have developed new alloys. For example, manganese bismuth free hard microwires. Here the important you see is the coercivity as a function of temperature. Coercivity is not so large. What is important is that coercivity increases with the temperature. Normally it has to decrease, but in this particular case, because of particular anisotropy, it increases with temperature. So you know the best material for hard magnetic material is neodymium argon boron, but the working temperature cannot go above 200 degrees centigrade, even is high. So in this very particular cases, it can be used this type of alloys. Or also, we have been able to fabricate Heusler and same memory alloys. Example here with the nickel manganese gallium glass coated microwires. Where some visiting person from China. Also, another applications were developed with a new family of magnetic wires, so-called B magnetic wires. So we start with a glass-coated microwire. We spattered a tiny layer, nano layer of gold, and then by electroplating, we grow an external layer, an external magnetic cell. So this is a cross-section of this B magnetic wire. This is the internal core, the pyrex in the middle, and the magnetic layer in the outside. So we have a magnetic wire with two magnetic materials inside. So the magnetic response can be something like that. So with two large Barkhausen jumps, depending on the particular magnetic behavior of the core and the cell. And that has been used for a number of applications. I would like to mention just one, I think one or two. So they have been used as temperature, actually thermometers. So for example, since the material is the temperature behavior of the internal magnetic layer, the external magnetic layer, and the pyrex is different with temperature because of the different thermal expansion coefficient. So when you increase a little bit the temperature, so the material, the microwire, bends a little bit. But it is actually is very significant, this bending, around room temperature for particular microwire composition and so on. And this is the amplitude of a bending, proportional to the radius of curvature as a function of increase of temperature around 25-30 degrees centigrade. So it's very sensitive to measure the temperature, and also the time of response is very fast. This is one of the last applications. It was in collaboration with Laura Lewis. Some of you, I'm sure you will remember her from Boston. Actually, I brought there a series of microwires, and they were interested in the magnetostimulated neuronal growth because they had previous measurements. They know that putting a neuron, a damaged neuron, in the presence of a magnetic field, they grow faster than without applied magnetic field. In our case, in addition to some magnetic field, a static magnetic field, I brought these microwires generating very local magnetic field. And the final result is summarized here in these statistics. The length of the neurite or neurons is the largest when we have a magnetic microwire plus a magnetic stimulation is that we have an additional magnetic field, a static magnetic field. So they are also still very interested to develop a new project to investigating further interest these applications. Well, although we still continue to investigate the motion of domain walls in the microwires, how is studied from this bistable behavior. This is still we can imagine many novel experiments, but I would like to emphasize that we have in the last 10-15 years, we have had a contrast with different companies, and because I know I emphasize this because it's not so usual, with different companies, international companies, and also many people is asking us to supply with these microwires for different applications in the center. So we have supplied these microwires for different universities and companies, also internationally. So I would like to emphasize this because it's not so usual. Let me have a bit of water. We start with the nanowires. Okay. There is an increasing interest recently to determine which is the role played by the curvature in nanostructures in the magnetic response, in their magnetic response. For example, as you know well, most of the technology is two-dimensional technology with thin films, multi-layers, but always in 2 dimensions. But what happens if we are able to generate some curvature? For example, if we are able to make a membrane to turn up, so we have a new material, new nanostructure. Or for example, this kind of multi-layer structure, or nanotubes or nanowires. Well, this, so in the screen is very, so I can show you this nanowire is vertical. Well, there is an increasing interest by different groups all over the world about the influence of the curvature. For example, these arrays of magnetic nanowires are very suitable to generate 3-dimensional architectures. So particularly, I would like to mention the racetrack array developed and proposed by Stuart Parkins. He is still working on that. He gave a talk in the Intermag in Rio de Janeiro a couple of weeks ago about that. It is important, the possibilities that we can have combining this electrochemical technique, I will mention later, with lithography, different lithography techniques. But these cylindrical nanowires are proposed currently by many different authors, groups, for many different applications, not only from the fundamental magnetic behavior, but also for many applications. Here is a summary, well, a review article. They are interested in this. Well, they are working about barcode or multi-segmented nanowires. I will be talking later for magnetic properties, based optical properties, electrical properties, but also on some applications that are not strictly magnetic in principle. For example, for catalytic applications or nanoswimmers. Nanoswimmers. So we are in contact with Salvador Panet in Zurich. So they fabricate very nice hybrid wires with a magnetic head and a polymeric piezoelectric tail. So they have very, very interesting properties for drug delivery or magnetic catheters and so on. But also I see Puerto is very interested in the biomedical applications. So this is for you. So there are some applications making use of these nanowires. In this case, the cell, the tumoral cell, likes to eat the nanowire. Once the nanowire is inside the cell, you apply a low frequency magnetic field, and by friction, actually not hyperthermia, so you can kill the cell. Also, some other applications, the group, for example, Luc Pirot in Belgium, so they are preparing arrays of nanowires, interconnected nanowires for thermomagnetic applications, or particularly the group in Minneapolis by Beth Stadler to make use of high frequency properties for identification applications. In our case, well, we have been working many years, no? Many years on these in cylindrical nanowires particularly. So why in the beginning we were working in that technique. These nanowires are prepared by electrochemical route. It is because it's cheap. It's very cheap. It's compared to other techniques, is much cheaper. And it is possible to obtain nanowires and nanotubes with very reproducible properties. And so we have been working a number of years on these materials. And as a summary, I can tell you that we can control the diameter of the nanowires roughly from 20 to 400 nanometers, and the length from around 60, 80 nanometers to 50 microns. So we can have really a very large, very high aspect ratio, length to diameter. So but first we prepare a porous membrane as a template. We prepare that in the laboratory, and then we fill the spores with nanowires. In the laboratory, we have prepared, particularly Cristina Brown, she's now in Zaragoza. She has been responsible for the fabrication of many different families of nanowires. For example, nanowires with homogeneous composition and diameter, but also modulated nanowires, where this modulation can be the longitudinal direction. For example, you see this is a cobalt gold multi-segmented nanowire, or in the radial direction. For example, you see can be nanotubes or core cell nanowires. This is a nickel, an array of nickel nanotubes, and these are isolated iron gold core cell wires. But this modulation can be also in the diameter. For example, we can control, you see an individual nanowire with alternated segments with different diameter, thin and thick diameter. Also, we prepare radial or cylindrical nanowires in a radial configuration. Here, I would like to emphasize, here we have Manuel Vázquez and Clever Pirota and David Navas. They actually set up this laboratory for the production of aluminum membranes and nanowires around 15 years ago, something like that. So from that time, we have been able to prepare by ourselves. We are autonomous in the production of so many different families of nanowires and nanotubes and so on. Very, very simply, I would like to say that we start with a highly pure aluminum foil, typically 1 inch in diameter, and then by two anodization processes, we get a membrane opened by both sides. Then we spatter a tiny gold of a layer gold, and then we use this gold layer for to be used as a electrode for the electrode deposition. We have a picture of cobalt nanowire arrays, and in the very last years we have been interested particularly in the study of individual nanowires. So for that we have to remove chemically first the aluminum membrane and the gold nanolayer, and we have millions of these nanowires, and this is a very tedious work to separate them by centrifugal forces. So finally it is possible to get an isolated nanowire, and then we study the magnetic properties of individual nanowires. Some other applications making use of this electrochemical route, well, it's an example in collaboration with different groups. So for example, these nickel nanowires inside polystyrene nanotubes, or large-scale nanopatterning by soft lithography, imprint plus electrodeposition, or highly ordered plasmonic gallium nanoparticles in the upper part of the aluminum membrane. Some other applications. So this was in collaboration with in an European project. For our task was to fabricate rare earth-free nanowires to be used eventually as alternative magnets. So actually the response is not so high, particularly because of the magnetostatic interactions between the nanowires. But in collaboration with a group of Michael Farley in Duisburg, we were able to increase these properties as magnets. But we prepare iron cobalt composition because of the high saturation magnetization of 2.3 Tesla and the high Curie temperature. Also, Rafa is here. He prepared a couple of patents. No, couple or at least one or two. Well, some other, in collaboration with Pepe Rivas in Santiago de Compostela, well, in the Institute of Nanotechnology in Braga, we developed with them, or actually they were using our nanowires as a T2 magnetic resonance imaging contrast agents. So the response was very nice. The problem is to get an amount large enough to be detectable, because it's much easier to prepare nanoparticles in a big amount compared to nanowires. Also, in collaboration with Jürgen Kossel from, now he's back in Austria, but they prepared a core cell iron magnetite nanowires. You see here, this is a function of some thermal treatment they did. So, because this, the magnetite, the external magnetite cell protects the material, the nanowires, and the internal core, the iron core, increase the magnetic signal. This also I would like to mention, although I am not an expert at all, in a collaboration with Margarida Fernandez from the University of Braga. They prepare magnetoelectric polymer nanowires composites with magnetically controlled antimicrobial activity. They were interested in develop a new alternatives to chemical products, because the overuse of antibiotics loses the efficacy of these antibiotics. So an alternative is to use this magnetoelectric effect in this composite piezoelectric polyvinyl fluoride PVDF polymer with incorporated nanowires. So they observe that the inhibition of growth of bacteria is very important using this magnetic activity of the nickel nanowires inside the polymer. Now I would like to show more specific work in the laboratory. You see, this here is a hysteresis loop in a squid magnetometer, the black points, and this is a magnetic force microscopy image by Agustina and Miriam. I don't remember who did particularly the measurement, but I put both. And you see there is a number of black and white points. Black and white indicates that the magnetization in each individual nanowire is pointing up or down. Okay, so you see in this is in a remanence state. Now I hope where is it? No, para atrás. As we apply the magnetic field perpendicular to the membrane, you see some black points become black. So they are individually reversing magnetization individually in each nanowire. So we can control, or we can observe even by this magnetic force microscopy technique, the evolution of the global magnetization, but also individual magnetization of nanowires. And you see this, by counting the number of black and white points, we can reproduce which is the net magnetization, these red points. So they are overlapping with the results with the squid. So in the case of nanowires, so I would like to emphasize that first, if we are working with cylindrical nanowires, for example, in permalloy has zero magnetostriction and zero magnetocrystalline anisotropy. So the only important anisotropy is the shape, is the length and the diameter. So depending on which is the length and diameter of the permalloy, for example, we have a ground state that can be where the magnetization in the axis can be axial or transversal in the plane. This is kind of aspirin. This is a long cylinder. And for this large area, we have a vortex configuration. In a vortex, the magnetization, the magnetic moments are circumferentially aligned. You see here also, but in the very axis. In the axis, we have, because of the exchange coupling, the magnetic moment has to be perpendicular to the plane of the vortex. More recently, as you know, the skyrmions have become very fashionable. In fact, skyrmion is a kind of vortex, but it's more complex, because we have in the very center, we have magnetization pointing down, for example, and in the very surface, magnetic moments are up oriented. So we have a transition in this area. So we have a skirmion, and up to, well, most of the work have been done in planar, in thin films. So we have a kind of, skirmion is a kind of nearly a dot, having this distribution of magnetic moments. But what happened in the case of our nanowires? In our nanowires, we can observe what is called a skirmion tube. So we have this skirmion that extend along the length of the nanowire. Okay, this most of the work on skirmions have been done from the theoretical point of view, but very recently, so we have been even more or less confirming this skirmion structure. But I would like to point out the difference between nanostrips and nanowires. In nanostrips, we can have a transverse domain wall separating two domains, axially magnetized, or this vortex structure. But in the case of cylindrical nanowires, well, we can have also these transverse domains, which is similar to the strips, but very differently, this vortex is actually becomes a block point domain wall. This is a very, how to say, unstable, it's metastable. So this requires a lot of energy, and as soon as it is formed, it tries to move to one end of the nanowire to be annihilated, because it creates a lot of energy. Well, this is an image, some micromagnetic simulation of a block point for the surface and in the inside. So here we have a zero axial magnetization. Well, if we can talk later if you are interested. But from now on, I'm going to talk only on last results on individual nanowires. You remember after being dissolved this aluminum membrane. And this, in this case, which is very different compared to the microwires, amorphous microwires, the crystalline structure is very important. It's very important because it can compete with the shape anisotropy. In fact, most of the nanowires we have fabricated, they have either cubic anisotropy, for example, those nanowires rich in iron or nickel, or we can have a hexagonal crystalline anisotropy, like pure cobalt or cobalt very rich nanowires. So, and I would like to emphasize that the hexagonal crystalline constant is much larger than the cubic. So the cubic anisotropy is overcome by the shape anisotropy. But the hexagonal anisotropy and the shape anisotropy, many times they have to be balanced because they are in the same order of magnitude. This is, so let me summarize for you. So the results for this is a cubic cobalt nickel nanowire with a large content of nickel, so it is cubic. And this is a magnetic force microscopy image. Agustina, or so you see this is an ideal magnetic dipole. This black and white contrast indicate that we have a very local distribution of magnetic charges at the ends of the nanowire. And then inside it is magnetization is homogeneous. This is a micromagnetic simulation, and this is an experimental hysteresis loop, this noisy loop, obtained by the magnetoptic Kerr effect that we have in the laboratory. So you see this behavior, these large Barkhausen jumps reminds one of the magnetic bistability of the microwires. So, so in fact, so when we apply the magnetic field anti-parallel to the magnetization here, we will have a kind of block point domain wall that moves very fast from one end to the other. But when we change the composition and we have a cobalt 85 nickel 15 with a large content of cobalt, we have a very different magnetic domain structure. For that, we have been making a number of studies in Barcelona in the ALBA synchrotron to investigate the domain structure and the domain process of individual nanowires. So in fact, we are profiting of this cylindrical shape of the nanowires. So we have the incident X-rays part of them are reflected, and this, the information in these reflected X-rays give us information of the magnetic moment distribution at the surface of the nanowire. But part of them are transmitted, and these transmitted X-rays give us information of the magnetic moment distribution inside the nanowires. So with this technique, it is possible to see magnetically inside the nanowires. So we can determine which is the distribution of magnetic moments inside the nanowire, not only in the surface. For example, this is an example of for this HCP hexagonal nanowire. You see this is completely different magnetic domain structure in different regions of the nanowire. Here we have a number of multi-domain structure, multi-domain transverse domains. Well, here we have these different contrasts is interpreted, consider that we have two magnetic vortices with different chirality. So one is magnetic moments are rotating in one direction, and the other is in the opposite direction. Also in collaboration with Etienne Snook in Toulouse, it was possible to correlate this local magnetic structure with these vortices with the local hexagonal crystalline structure of the nanowires. So the red part is the hexagonal, and the blue is FCC. So we have this exotic vortex domain structure just in the region where we have hexagonal symmetry. Also, we were able, in collaboration with people in Dresden, to obtain this, it is the same information as we got there. Now we go to the last part of the talk, giving some results of the modulations in diameter nanowires. You see these two types of modulations. I like very much this image obtained in Toulouse. You see, this is a nanowire with this and the thin region of the diameter between two large diameter segments. So these colorful regions correspond to the induction magnetic field outside the nanowire. So we are observing the lines of magnetic field outside the nanowire. So you see that in the transition of diameter, we can observe that there is accumulation of magnetic charges generating the field outside. Also, particularly with Oksana, has been supervising all these micromagnetic simulations aspects, and Jose Ángel Fernández Roldán, they did a number of micromagnetic simulations in these diameter modulated nanowires. It was possible to identify the presence of skyrmion tubes from the micromagnetic point of view, where the axis of the skyrmions is not completely always in the center, but is making some helical motion along the length of the large segmented, large diameter segments. This is a very recent, I would like to show you this because it's not yet published. It's in collaboration with Umberto Celano, who has been working with this company and now is in Arizona State, with this fashionable technique, the scanning nitrogen vacancy magnetometer. So you see this is the nanowire prepared by Cristina, and it was, with this technique, it's possible to resolve the distribution of these, what he called defects, but these defects are designed in the nanowire. And this is a map of the magnetic field along the length of the nanowire. So this technique is very novel technique and probably requires a further improvement. And the very, very last part, so it's my menor 10, so is this about the compositional modulated nanowires. There are two types of compositions. One is ferromagnetic 1, ferromagnetic 2, having cubic and hexagonal crystalline structure to obtain a modulation in magnetocrystalline anisotropy. And the other family is ferromagnetic and metal. So two magnetic segments separated by a metal. So these images were obtained in a cobalt nickel multi-segmented nanowire. So both are magnetic but one is hexagonal and the other is cubic. You see, this is a topographic image. They are very well resolved, the cobalt nickel and the nickel segments. And this is the magnetic image obtained in the synchrotron. So in the nickel segments, magnetization is axially oriented, but in the cobalt nickel segments, we observe vortices, and can be controlled by the length of these segments, etc. Also, there have been some simulations. I will not be talking now. And it's also very recent result. So particularly Rafa was involved in this study with a new technique, transmission X-ray microscopy, also in alpha synchrotron. You see this is an image of the nanowire. In this technique, it is possible to determine very clearly the distribution of magnetic moments, not only along the length of the nanowire, but also in the radial direction. So it is important, again, it is possible to determine the distribution of magnetic moments inside the nanowire. And the last experiment I wanted to mention is this nanowires, magnetic nanowires separated by copper segments, but you see the white lines correspond to the copper, and these copper segments are separating ferromagnetic segments. But interestingly, here is that the nanowire was designed so that in one end of the nanowire, the length of these ferromagnetic segments is much smaller than in the other end. So the length of the segments increases from one end to the other. This is a magnetic force microscopy from the end of the nanowire in the remanence, and it was observed by magnetic force microscopy that the reversal of magnetization started in the end with the smaller segments. And this was confirmed, even more investigated. We were able to get more information with the PEEM images with the circular decreasing analysis. We observed what we call magnetization ratchet. So under a negative field of -700 Ørsted, we have a white contrast. So the white is practically saturated magnetically. And as we apply a positive field with increasing amplitude, we observe that the reversed domains increase in size until getting the opposite saturation. But interestingly is that the reversal starts in the end of the nanowire with the smaller magnetic segments. But if we start with the opposite saturation on the positive field and we apply a negative field, again we observe the reversal of magnetization starting from the same end. So this is why we call it ratchet, magnetization ratchet, because reversal starts always from the same end. So it is possible to reconstruct the hysteresis loop of this nanowire with this experiment. This unidirectional reversal process has been interpreted with the macromagnetic simulations. You see here a small video. So this is one end with the small segments. Reversal, the change of color starts always from this end. Okay, this is a typical mechanical ratchet, which is known from many years ago. And I think I stop here. I have a couple. If you are interested in some effect on magnetotransport properties or influence of current, I will be happy to mention later. But I think this image is very important. This picture is very important because this work I have mentioned represents the work of the group during many years. So it's not only me, but it's people like Agustina, Rafa, Oksana, David. So this is a picture just before the COVID, and it's a more recent picture. Okay, thank you very much.
Thank you very much for this nice overview about your work in micro and nanowires. And now it's time for questions.
Allí.
you cover these wires with a superconductor? Is it possible to do that?
You're thinking of nanowires. So in fact, to fabricate these nanowires is if you have a superconductor that can be grown by electrodeposition, or yes, but we haven't done this. But this is really that would be very interesting to have a magnetic nanowire also with superconducting properties. But actually, I do not know of any work like that.
Okay.
With this type of material.
So maybe if it's even possible or not, no?
Well, it depends.
Or it should be.
For the electrodeposition, you need a metallic material. So that's why we are working with iron, nickel, cobalt, or copper, but always metallic elements. Also, well, we have done also some collaboration with people in Oviedo. They have ALD, so you can prepare core cell nanowires where the cell can be fabricated by atomic layer deposition. But I am not sure about the composition of these superconductors. Actually, I think that would be a very, very nice, very interesting work. But for the moment, we have not
Thank you.
been able.
More questions? Well, I will start with a question. You have shown in the last 40 years, you have seen how you start to measure the fundamental properties of microwires, and finally you show us the many applications, real applications that have the microwires. What about the nanowires? Do you think that some of these applications will be in the future in a real device?
Yeah, in fact, I think that's different group, particularly Ben Stadler in Minneapolis. They are doing a very nice work with the real applications for identification at high frequency, on also biomagnetic applications, but always with arrays of nanowires. When the nanowires are inside the membrane. So, because the nanowires, individual isolated nanowires, are much more difficult to manipulate. So, but for example, this application with the nanorobots or swimmers, this is with individual nanowires, composite or hybrid nanowires. So I'm sure. So up to now, many more people are asking about the microwires for sensing elements of different magnetic sensors or temperature sensors or stress sensors. But with nanowires, not so many people. They are still interested in collaboration to characterize the magnetic properties of particular nanowires with particular composition. But I am sure that in the near future there will be much success in the real applications of the nanowires.
More questions? No? Well, then thanks again, Manuel.
Okay.